Hello and welcome to the first video of the M2 chapter, Projectiles. On the screen, an M1 question to review this idea that we're going to be using a lot through this chapter and through this entire module. Write down the constant acceleration formulae, and then there's a projection question as well. So the constant acceleration formulae you should be familiar with from M1. We've got v squared equals u squared plus 2as, s equals ut plus a half at squared, which we're going to use a lot in this video. S equals vt minus a half at squared. V equals u plus at. And finally, s equals a half u plus v times t. Here we've got a ball projected vertically upwards, modelled as a particle moving freely under gravity. We'll come back to that phrase in this video. If the initial speed of the ball is 12 meters a second, find the maximum height of the ball above its starting point and the time taken for the ball to return to its starting point. This sort of question should be very familiar to you, so I'll just highlight the really important bits. First, you need to make sure you're clear which direction you're taking as positive. For part 1 of this, I'm going to take the upwards direction as positive. That means when I list my information, the acceleration is going to be minus 9.8 because gravity always acts vertically downwards. It's going up with an initial speed, so this is positive, the initial speed 12 meters per second. And if we want to find the maximum height of the ball, that's when it gets to an instantaneous rest point, and the velocity will be 0 just for a moment. These are the 3 bits of information we know. What we want to find is the maximum height, that's s, so we pick the appropriate formula to find s when we know these other 3 things here. And in this case, we can use the first one. So putting in those numbers, we get 0 squared equals 12 squared plus 2 times minus 9.8 times s, which is the thing we want. If I take that second term on the left-hand side, that gives me 19.6 s is equal to 144. Divide through, and we get s is equal to 7.35, rounded to 2 decimal places. We're using standard units throughout, so this is meters. For part 2, I'll do this in a different colour. Remember, this is a separate calculation. So that's completely separate. We need to start all over again. I'm going to take, just because I can, let's take the downwards direction as positive this time. List the information I've got in this situation. A is still acting vertically downwards. So because I've chosen downwards to be positive, that's now 9.8 instead of minus 9.8. My initial speed is still acting upwards, so that's the negative direction now. And you might say, well, why have you changed? And there's no reason there. I've just changed to show that you can choose the downward direction as positive. There's no benefit particularly, just showing that it can be done either way. In this question, though, we need to find the time taken for the ball to return to its starting point. So from the time it's projected upwards to the time it comes back to this starting point, overall, talking about vectors, displacement, not distance, the displacement here will be 0 because it will be back where it started. And we need to find the time. The equation I'm using this time does not have a v, so it's this one here, s, u, t, and a. Put the information in. T is just t, I don't know what that is yet, plus a half of 9.8 t squared. And you'll see that we've got a quadratic here. We're going to have 2 answers. I expect one of those answers to be 0, because obviously it's at its starting point when it starts its upward journey, and then it comes back to that starting point later, so one of these t's will be 0, and the other one is the one that I want. We can see that very quickly by factorizing out the t here. So this gives me t equals 0, which is true, but isn't the one I want. And this gives me t is equal to 12 divided by 4.9, which is 2.45, again to 2 decimal places. And again, because we've used standard units throughout, that is seconds. So before we get into the M2 chapter, I hope you're really confident with this sort of question, because this is the absolute foundation point of this whole chapter. If any of that you weren't quite sure on, I would suggest you go away and review this topic from M1 before you start M2. So the overview of the chapter, we're going to solve problems involving motion under gravity, which is pretty much what we just did, but slightly differently. We're going to have horizontal motion in these projectiles, which we didn't have in that starter question. Resolve velocity components, because we won't be having just vertical motion, so there'll be components vertically and horizontally. Solve problems involving projection at an angle, so it'll be using this idea, resolving the initial velocity in order to solve the problem. And then we'll derive and use projectile motion formulae, which aren't all that useful really, but you might be asked to derive one of these in the exam, so you need to know how to do it. So let's kick this off by solving problems involving motion under gravity, just what we did there in the starter question, but with some horizontal motion thrown in as well. So as in M1, if we model a particle as moving under gravity only, that was the phrase we had in the starter question, it means that we ignore all other factors. We're not worried about air resistance, we're not worried about the spin of the particle or anything like that. We're only interested in gravity. That's the only force acting. And of course on Earth that's completely unrealistic, but it's a decent model because it gives us a good approximation. And then if you're working on models like this, you would take it a step further, you would add in air resistance later, and then you could take it a step further and add in other stuff as well. So this is like a basic model. This means the only force acting is gravity, as I just said, so the only acceleration is due to gravity and is vertically downwards at 9.8 meters a second, which is what you're familiar with from M1 and what we did in the starter question. However, this does not mean that there is only vertical movement and nothing else. An object can be moving horizontally by having an initial horizontal velocity and yet be acted on by gravity only. What that means is, if it only has a vertical acceleration, the horizontal velocity, if there is any, will stay constant throughout the question. So you can still use your constant acceleration formulae, but in the horizontal component, the acceleration will always be 0, which is actually really good because it makes a lot of the equations far simpler. And it emphasizes that you have to consider these two things separately. The vertical motion and the horizontal motion have to be completely separate. So one of the key points here is to remember that objects moving under gravity, the horizontal and vertical components are independent of one another. So those few notes there, this key point here, and all the knowledge that you've had from M1 that we had a quick review of in the starter question, that's it for the notes on this section. Let's get into a few examples and you'll see how this works. A particle is projected horizontally at 25 meters a second from a point 78.4 meters above a horizontal surface. Now I'll say this many times through these mechanics videos, draw a diagram. This is really key for helping you to see what is going on. And sometimes it's less important than other times, but it's a really good habit to get into. Draw a diagram. I once went to a conference with maths teachers and we had all the mechanics teachers in one group, and somebody asked the question, what's the one thing you have to say to your students again and again? And almost everybody in the circle said, draw a diagram. It can be really useful. So here we've got a vertical distance above horizontal ground of 78.4 meters. The particle here is being projected horizontally at 25 meters a second. Now that might not seem like a lot of information, but remember, if it's moving under gravity only, which it doesn't specifically say in the question, but we're assuming it is, then we know the acceleration as well. The acceleration in the horizontal direction is 0. The acceleration, once it is projected off this, whatever this is, cliff or whatever, then the acceleration vertically will be 9.8 downwards. So we've got that acceleration information as well. Find the time taken by the particle to reach the surface. So once it's projected off of here, it's going to follow a parabolic trajectory like this, come down and hit the ground somewhere down here. And the time that takes, although it might be unintuitive to you, the time that takes is completely independent of this speed here. It does not matter what this speed is. The time it takes to go from here to hit the horizontal ground is all about how quickly it drops. And you might have heard this example before. If you fire a bullet from a gun and you drop a bullet from the same height, if you were able to ignore air resistance, which isn't very realistic in that sort of situation, but if you did, they would hit the ground at the same time, even though the bullet fired from the gun would be a lot further along horizontally. They would strike the ground at the same time, because this drop here is only dependent on the vertical acceleration. Okay, that's enough hammering on that. Let's actually do the calculation here. So the acceleration downwards, of course, is 9.8. Now I need to be a little bit careful here about my direction that I'm choosing to be positive. What I'm going to do, because the acceleration is acting downwards, and starting from this point, dropping down, this is going to be a downward displacement from here to here, or a vertical displacement from here to here, I should say. So the displacement and the acceleration are acting downwards, so to try and minimize the number of negatives in my question, I'll make down my positive direction. On questions like this, I also need to be clear for the examiner whether I'm doing the horizontal bit or the vertical bit, because they're so separate. So what I'm going to do here is put a big old R, and that for me stands for resolving. I'm resolving downwards. And then I don't even need to do this bit here, because the arrow in the brackets there is my positive direction. So this means resolving, and downwards is going to be my positive. That's what I mean when I write that. So resolving downwards, we've got acceleration is 9.8. The displacement is 78.4 from the question. The initial vertical velocity is 0. All of the velocity is acting horizontally initially. In a later video, we'll look at questions where there is some vertical and horizontal velocity, where it's projected at an angle, but in this case, the vertical velocity is 0 to begin with. And then we just need the time. So normally I put a question mark there, but I shouldn't really do that, should I? I should put t is equal to t, because that's the variable I'm going to put into my equation. And the equation I'm going to use here is s is equal to ut plus a half at squared. And u is 0, so this term here becomes a 0. And we get 78.4 is equal to a half of 9.8, 4.9 t squared. Obviously, I'm going to take the positive root for time. We're not going to have a negative time here. And if I put that on my calculator, they've chosen these slightly awkward numbers because it gives you a really nice square root. It's just 16, so that gives me 4 seconds. And there we go. Part A finished. Part B. Find the horizontal distance travelled in that time. Now, I've said that the horizontal and the vertical motion are completely independent, but I hope it's obvious that the time taken is one thing that they do share. So the time it takes for the particle to move vertically 78.4 meters, i.e. to get here vertically, is the same time it takes for the particle to move here, however far it's moved horizontally. The other information we have horizontally is 25 meters a second to the right, and the acceleration horizontally is 0. So let me write this down. I'll follow the same sort of pattern each time, resolving, list the information, equation, calculation. So part B, I'm resolving, and I'm going to go horizontally taking the direction to the right as positive. When I do this, I've got time 4 seconds, because I know that we want to look at going from this point to this point. So that's 4 seconds from part A. We know that the initial velocity is 25, and the acceleration horizontally is 0. And the question wants the distance travelled in that time, so the displacement s, we could say, is equal to s. Then our formula, same one, s equals ut plus a half a t squared, and you can see how this makes it easier having the acceleration as 0, because if a is 0, this whole term here is 0. And we fall back onto the old favourite distance equals velocity times time. And in this case, the velocity 25, the time 4, gives us a nice round 100 meters for the distance travelled horizontally. So that's from here to here, 100 meters. That's it for our first example. Second example, particle is projected horizontally with a velocity of 15 meters a second. It doesn't tell us how far above the ground that is, but assuming motion under gravity assumes that it doesn't start on the ground. So I'll take an indefinite height and just project it off of here, this way, 15 meters a second. Find the horizontal and vertical components of the displacement, so we're looking for distance here, of the particle from the point of projection after 3 seconds. So it's saying horizontal and vertical components because 3 seconds is shared between the horizontal and vertical parts, but they're separate calculations, so I need to look at the distances or the displacements separately. So let's say it's projected, and again it moves parabolically, and after 3 seconds, let's say it's down here somewhere. The question is, what is the horizontal distance, the horizontal component of the displacement, and what is the vertical distance, the vertical component of the displacement? And we have to take these two questions separately. Resolving vertically, again I'll choose downwards as positive. We have acceleration is equal to 9.8. The initial speed downwards is 0. And of course we know the time is 3 seconds for both horizontal and vertical. Then we're looking for s. So we're using that same formula again. Put it all in. We get a 0 plus a half times 9.8 times 3 squared, which gives us 44.1 meters for the vertical component of the displacement. Then we have to do it again, but horizontally, and again I'll take the positive direction to be the right direction. So we have u is equal to 15, a is equal to 0, t is still equal to 3, and s is what we want. So we're using, again, s equals ut plus a half at squared, where a half at squared becomes 0. So s is equal to u 15 times 3, and that gives us 45 meters. So my diagram is not very good. The horizontal distance is only slightly bigger than the vertical distance. That's it for part A. Part B, we need to find the distance of the particle from the point of projection after 3 seconds. And you might immediately think, well, we just did that. And we have. But what we found is the horizontal component and the vertical component, and what this is asking for is the diagonal distance here. And of course you can see that we've got a right angle triangle there. All this is asking us to do, if this is part A, in part B, all it's asking us to do is to use Pythagoras. So we've got 44.1 squared plus 45 squared. The square root of that gives us the absolute distance from this point to this point. And of course that's very different from the distance travelled, which would be this arc of a parabolic curve here. It just wants the distance from here to here in a straight line. And when I put that on my calculator, I get the answer 63.0064 ... put that down first just to show that it's not exact, but when I round it, it's going to be 63 to the nearest meter. Example 2 finished. Example 3, final example of the video. A particle is projected horizontally with a speed of u meters a second from a point 122 meters above a horizontal plane. So as with the other ones, I'll get my diagram going here. I know this is horizontal down here. This is 122.5 meters from here to here. In this case, we've got the particle projected horizontally but with an unknown speed. We're also told that the particle hits the plane at a point which is at a horizontal distance of 90 meters from the starting point. Horizontal distance of 90 meters. So let's put that here. Oh, again, my diagram's not very good. That 90 looks like it's bigger than 122.5. I should say not to scale on this, shouldn't I? So this comes down parabolic. That's not very parabolic either. Oh dear. Forgive my drawing. And it hits here. The question then is find the initial speed of the particle. This question is giving an example of how the fact that time is the same between the two components is very useful. To find the horizontal velocity with nothing more than the horizontal distance, and of course the acceleration, which we know is 0 horizontally, that's not enough information. I need another piece of information. I need at least 3 bits of information to find a fourth. But what I can do is use the time, and I can find the time by looking vertically first, because vertically we know the displacement, we know the acceleration, and we know the initial velocity vertically is 0. So we know displacement, acceleration, and initial velocity, which gives me enough information to find the time vertically, and the time is the one thing that is also the same horizontally. So then I can use the time to resolve horizontally and find u. So this is a 2-stage process. First I need to resolve vertically, not because the question wants that, but because I need to find the time. We've got a is equal to 9.8 downwards. We've got u is equal to 0. S is equal to 122.5 downwards, so that's positive again. And t is the important thing I'm trying to find to help me with the horizontal bit. Same formula again. S equals ut plus a half at squared. U is 0, so we get 122.5 is equal to 0 plus a half times 9.8, that's 4.9 t squared. Remembering t must be positive, and putting that on my calculator gives me a really nice answer. I suspect the numbers were very carefully chosen there to give an exact 5 seconds for the time. Now I can take that time and use it in the horizontal to find the missing u. So let's resolve to the right. We've got u is equal to capital U given in the question. S from the question is 90. A horizontally is 0. And we now know the time when it strikes the ground is 5 seconds. So it's the same formula again, S equals ut plus a half at squared, where a is 0, so this becomes 0. So when we put the numbers in, we get a 90 here, 5 for the time, and u, which gives u to be 18 meters a second. And there we go. I hope that's enough information for you now to have a go at the questions from exercise 1A, and maybe I'll see you in the next video.